Hi, in this video we are going to derive the Fourier transform of the unit step signal. So U of t denotes the unit step signal, which is equal to 1 for t greater than 0 and 0 for t less than 0. In terms of the Fourier transform, the value at t equal to 0 is not important at all because in integration a single point will not contribute. Therefore, we can just assume we have an equality here. For t greater than or equal to 0, it is 1, and for t less than 0, it is 0. Now, first of all, we have to remember the following. This signal is not an absolutely integrable signal. Okay? So, from minus infinity to plus infinity, magnitude of u of t integrated with respect to t is simply from 0 to infinity the integral of 1. But this is not a convergent integral, so the integral diverges. By divergence we mean the following. We first evaluate the integral from 0 to, say, a certain value, a finite value. Of course, that integral exists. But if that value tends to infinity, we have divergence. So, u of t is not absolutely integrable. Therefore, its Fourier transform does not exist in the sense that the Fourier integral exists. The Fourier integral does not exist because x of t is not absolutely integrable. But remember, we have seen some cases where this condition is not satisfied, but still we can find the Fourier transform. But in that case, the Fourier transform becomes infinite at certain frequencies, at a single frequency or at multiple frequencies. So this is such a case. We are going to see that we will be able to obtain an expression for the Fourier transform of u of t, but that Fourier transform will not be finite for all frequencies from minus infinity to plus infinity, but at certain frequencies we have infinite magnitude. So let us see how we can achieve this. Now, u of t can be decomposed as its even part and its odd part. Okay. Now, the even part of u of t is just equal to 1 over 2. Okay? And the odd part of u of t is equal to 1 over 2 for positive values of t and minus 1 over 2 for negative values of t. Here we may have an equality, or we may just omit the equalities and write it as inequalities. So this u of t can be decomposed as the superposition of its even and odd parts. Now the Fourier transform of the even part of u of t is 1 over 2 times the, remember the Fourier transform of 1 is 2 pi delta of omega. So this becomes pi delta of omega. And here we observe that now we have an infinite magnitude of the Fourier transform at omega equal to 0. This is due to the fact that u of t is not absolutely integrable. Therefore, we do not expect that its Fourier transform in magnitude is finite for all omega between minus infinity and plus infinity. And here we observe that, in fact, at omega equal to 0, we have an infinite magnitude of the Fourier transform coming from the even part. Now, how can we evaluate the Fourier transform of the odd part of the unit step signal? Okay, now at this point we can use a limiting operation as follows. Consider the signal x of t equal to e to minus alpha t u of t, where alpha is a positive constant. In fact, we see that limit as alpha tends to 0 of x of t is u of t. And limit of the even and odd parts of x of t as alpha tends to 0 will be the even and odd parts of u of t. Now we see this from the odd part. Okay, let us see the odd part of, remember the odd part of x of t. So this is the odd part of x of t. It is equal to the decaying exponential function for positive values of t starting from 1 over 2. And then for negative t, we have also a decaying exponential, but now we have this decaying exponential becomes equal to minus 1 over 2 at t equal to 0. And when alpha tends to 0, this odd part of x of t tends to the odd part of u of t, which is equal to this signal in graphical form. Now, x of omega is, remember, 1 over alpha plus j omega. So it is equal to alpha minus j omega divided by alpha square plus omega square. So Fourier transform of the odd part of x of t is minus j omega divided by alpha square plus omega square. So when alpha tends to 0, limit as alpha tends to 0 of x odd of omega is equal to minus j omega over omega square. So this is equal to 1 over j omega. Remember, minus j is equal to 1 over j. So this is just the Fourier transform of odd part of u of t. Okay, so the Fourier transform of u of t is can be written as the Fourier transform of the odd part of u of t plus the Fourier transform of the even part of u of t. Now, Fourier transform of the odd part has been calculated as 1 over j omega, and the Fourier transform of the even part is pi delta of omega. Okay, we clearly see that the properties satisfied by the Fourier transforms of the even and odd parts are satisfied. That means the Fourier transform of the odd part is odd and pure imaginary, and the Fourier transform of the even part is real valued and even. Okay, so we have calculated the Fourier transform of u of t, but not by using the integral expression of the Fourier transform, because u of t is not absolutely integrable, and therefore the Fourier integral is not a convergent integral. But we have calculated this result by using certain tricks. In fact, we clearly see the infinities in the Fourier transform. We have an impulse at omega equal to 0, meaning that at omega equal to 0 we have an infinite magnitude. And also this 1 over j omega is not bounded for all omega, but it when omega tends to 0 in magnitude, it diverges. So this divergence is due to the fact that u of t is not absolutely integrable, so its Fourier transform does not exist in the classical sense. That means in terms of the Fourier integral, but we have obtained this result by using the tricks we have involved in the derivation. Now, we know that the derivative of u of t is the impulse. Now, remember the differentiation property by using the differentiation property of the Fourier transform. A Fourier transform of the derivative of u of t is equal to j omega. Remember, differentiation in time domain corresponds to a multiplication by j omega in Fourier domain. So j omega times 1 over j omega plus pi delta of omega. So we have 1 plus pi j omega delta of omega. But remember, the action of the, when you multiply a function by an impulse, you have to evaluate that function only at the point where the impulse strikes. So this is omega equal to 0, and when omega is equal to 0, this becomes 0. So this term reduces to 0 because of the omega appearing as a multiplier of the impulse. So we have the Fourier transform of the derivative of the unit step is equal to 1, which is nothing but the Fourier transform of the impulse. Okay, so we can stop at this point. Thanks for watching.